In Part 1, I discussed the Objective-C language in brief. Now let's talk about the UIKit framework. UIKit, or Cocoa Touch, is the main framework used in iPhone app development. A framework is a library of code that has already been compiled into binary, so you can't mess with it, but you can include it in your projects and use it according to a set of rules called an API, or Application Programming Interface. Most of what UIKit consists of is a bunch of compound data types, that is, objects that consist of a few commonly used data structures, and all of the methods that would be appropriate to the creation and use of such a data structure. This can be anything from a simple NS-string object to the highly complex UI table view class. Particularly useful are all of the user interface or UI classes like UI button, which does all of the work of creating a button for you. In fact, the setup of these UI objects is made even easier since they are available as little icons in Interface Builder's library, which can be dragged and dropped into the project window. Interface Builder is a part of the SDK that you use to create the UI out of UIKit classes. It provides a graphical interface for doing this and stores your work in a graphical format, .zib in XML form, or .nib in binary form after compilation. This approach makes sense since you are creating an inherently graphical entity, though it can be tricky to get used to thinking about these graphical entities in terms of their underlying code counterparts, which is what you deal with in Xcode. IB is particularly useful for setting up connections, that is, target action relationships, between on-screen controls like buttons and text fields and their associated methods in the underlying code. Unfortunately, Metronome doesn't provide any good examples of IB in action, since they use the nib files just to do the bare minimum of work, that is, creating the app delegate and the view instances. This brings up the final topic that I want to cover, which is how does an application actually run? You need to understand this in order to get started with reading sample code, which is the best way to learn iPhone programming. Recall that the compiler takes this sample code and translates it into something, a binary file, that a CPU can correctly execute. This binary file contains a bunch of data structures that will be used to store pieces of information, and a list of instructions that will be executed by the CPU. That's why it's called a program, because it's a list of scheduled events in the order in which they're supposed to occur, like a program of a wedding or something. In very simple programs, the events occur in a stereotyped manner. That is, there is only one possible sequence of instructions. For example, in the /bin directory, there's the date command, which prints out the current date and time. If we look at the binary using the otool command, we find that it actually requires a fairly lengthy set of instructions to accomplish this task. Most programs, however, are much more complicated than that, since they involve some form of user input, which means that the binary needs to contain all of the blocks of code that would be needed to respond to every possible user input. Fortunately, you don't have to write all of this code yourself, since the UIKit framework already contains code for all kinds of events and user interactions. In order to understand how an application runs, it is helpful to approach the analysis of a piece of sample code by reconstructing the flow of events that occur during program execution. So we'll start with a main function, which is the entry point for C-based applications. This means that this code is executed first. When it gets to this line, the UI application main function is called, which creates a UI application object and transfers control to it. We can't see inside of the UI application class because it's part of the framework, but we do know that it opens the main nib file, which is whatever is listed here in the info.plist file, in this case mainwindow.nib. The contents of this file are loaded into memory, which consists of the main window object, which the iPhone OS will put into place on the display screen, and this instance of the appDelegate class. The creation of the appDelegate object involves laying out all the appropriate memory space for its instance variables and setting their initial values, as well as loading in the instruction sequences that correspond to the methods of the object. Remember, this also includes all of the classes that it inherits from, like NSObject. During the creation process, an object will be sent a message telling it to initialize itself. This will actually be a series of different messages since an object has to initialize all of its component parts. The appDelegate class will first respond to the initialize signal, which means that this code will be run. Notice in the first line there are a couple calls to the class method, which doesn't appear to be in this appDelegate class because there is no corresponding implementation code in this file, so it must be from one of the parent classes, and we see it's part of NSObject, which is one of the objects that goes into making the appDelegate class. This is why this is able to work. The next line calls on the NSNumber class, which is part of the framework, and sets up the default time signature. The next couple of lines pull up the user defaults from a data file. At this point, the function returns, which means control is returned to the class that called it, which was UI application. UI application is the master object that governs the flow of control in a running application, by serving as the interface between the iPhone operating system and the application, which it sends a series of messages or notifications directed at the main delegate object, which is specified here in the main window.nib file, which was loaded earlier. Here the file's owner, which is none other than the UI application class, has its delegate outlet set to the metronome app delegate class, which means that UI application will send its notification messages first to the app delegate in case it or any of its parents contain any method with the same signature, in which case UI application will turn over control to the app delegate class and that method will be executed. The first message with a matching implementation is application did finish launching, and this is where it starts to get interesting. An instance of the root view controller class is created, which means we need to pause at this line and move over to root view controller's header. We don't see either the alloc or init methods here, so just like before, the hierarchy must be searched, and a match is found in the NSObject class. Alloc causes space for this data structure to be claimed from the memory, and the init message sets initial values for any instance variables that the class might contain. When the init method is done, it returns control to the calling function, which then continues executing. The next line of interest is this one, which will add a view object to the display window. This is the first thing that the user will be able to see happening. But to get to that point, several things must first occur. These message calls are read from the inside out, meaning before a message can be sent to window telling it to add a subview to itself, exactly what that view is, that is, what the memory address for the data that makes up that view, must be determined first. So the root view controller instance is sent a message asking for its view. And once again, no view method is found there, so the hierarchy is searched and a match is found in UI view controller. Right away we notice a couple things. First, this is actually a property and not an instance method, so the message was sent using the older syntax, making it look like a method. It doesn't matter, we can go back and change it if we want to. The other thing that may not be so obvious is that we never specified what the view was during the initialization of the root view controller instance. So the root view controller instance will be sent a load view message, followed by a view did load message, and this has a match in the root view controller class, and this is how that view got set. So control will be transferred to this method, and as you can see, it is almost identical to what is happening in the application did finish launching method in the app delegate class. So we can now see what is happening. The window loads blank, it loads the root view controller's view, which is also blank, and that in turn is filled with the metronome view, which actually contains something visible. And the reason it contains something is because it is properly initialized by the loading of the nib file, at which time this metronome view instance will be created, causing the metronome view object to be laid into memory according to the header file, and the initialization will be performed, which will create all of the stuff that appears on the screen at launch time. Control will now be passed back up the line to the statement that started this whole sequence, the one that asked the root view controller for its view. The rest of this function will execute and control will be returned to the UI application object, which will just sit there and wait for the user to do something. In this case, it could be one of a few possibilities. The user might press the iPhone's home button to terminate the application, in which case this message will be sent by UI application, and the app delegate class will respond to it, saving the user defaults, and then returning control to UI application, which then finishes terminating. Alternately, the user might rotate the iPhone, which would send this message, or the user might press on the info button, which triggers the toggle view method, which we already discussed, or the user might touch the screen, which will trigger these methods in succession. And these methods will in turn call a bunch of methods internal to the metronome view class that simulate the movement of the metronome's arm. And that's how an iPhone application runs. This ends this video.